All right, you ready to solve a mixing problem with integrating factors? I hope I am, because I have not solved this problem before. So we've done some mixing problems, and mixing problems are very powerful in terms of like fluid dynamics, and they can model a lot of ecological things as well. We're going to look at one of those today. And if the flow out of the reservoir or box or tank or whatever, if the flow out is the same as the flow in, we get an autonomous differential equation. Autonomous is nice, it's always separable, and we can do powerful things with autonomous differential equations. Now, if the flow is not the same, it's no longer autonomous, and that's what we're going to look at today. So this comes from the textbook. So let's say that we're considering a pond that has, I'm going to switch this to white. Let's say that we're looking at a pond that initially holds 10,000 cubic meters of water. Water not often measured in cubic meters, but it's going to make the problem a little nicer. All right, so again, our volume initially has 10,000 cubic meters of water, but that will change. So initially, the water in the pond is clean, and the pond has two streams flowing in, A and B, and one stream flowing out, stream C. So suppose 500 cubic meters per day of water flow in from stream A. Okay, 500 cubic meters of water are flowing in, and what else do we have? 750 cubic meters is flowing in over here. All right, so again, October, cats, man. All right, so what else do we know? And 1250 cubic meters flow out. Now, the astute mathematician may notice, you say, Jason, you said we're going to talk about something that's non-homogeneous. The flow in is not the same as the flow out. Well, don't worry. There's a bad ending to this story, because it's not just water that we're going to look at today. All right. So at time t equals 0, so this is the good news, the first paragraph. The bad news is in the second paragraph. At time t equals 0, the water flowing in the pond from stream A becomes contaminated with road salt. All right, so there's road salt being used to make the road conditions safer, and specifically it's at a concentration of 5 kilograms per 1,000 cubic meters. So we have 5 kilograms of salt per 1,000 cubic meters of water. This is our concentration. The water in the pond is well mixed. Okay, so again, we don't have to worry about any mixing, any actual fluid dynamics really. And so we can assume that the concentration of salt is constant in the pond. And apparently we have more bad news. Also at time t equals 0, someone begins dumping trash into the pond directly. So we have salt coming in from here. We also have people just randomly dumping in trash. So we have 50 meters cubed of trash. Don't do that. Don't dump your trash into the pond. All right. 50 cubic meters per day. The trash settles to the bottom of the pond, reducing the volume of the pond by 50 cubic meters per day. Okay. So even though the flow in is the same as the flow out, the trash is taking up that space. So the total amount of water in the pond is changing. All right, we're losing 50 cubic meters of water in the pond every day. Okay, this is per day. Well, let's just write per day. So that's the conclusion there. To adjust for the incoming trash, the rate that water flows out via the stream increases to 1,300 cubic meters per day so that the banks don't overflow. All right. So again, in some sense, the volume's still constant. right? The volume of the water plus the trash is still constant, but just the volume of the water is no longer constant. The volume of the water is changing in this factor. So, okay, I didn't trick you. More water is flowing out than is flowing in because trash is taking up that space. And so specifically what I'm going to be asking you to do is I want you to find the amount of salt in the water at t days. Again, the amount of salt in kilograms. You cannot see that, but I wrote in kilograms. So we're going to set this up with a differential equation, and then we're going to solve this differential equation. How are we going to solve it? Your guess is as good as mine. So what do we know here? Well, again, let's call this amount of salt S of t. All right, that'll be the amount in kilograms of salt, day t. T days in. So we know some things, right? We know what S of 0 is. We have our initial condition. How much was it? Well, initially the pond was clean and it was unsalted and it was untrashed. On day 0, everything was great. And we also know some things about the rate of change of salt, right? The rate of change of the salt per day is going to be the salt in minus the salt out. So how much salt is coming in every day? Well, we know that it's 5 kilograms of salt per 1,000 cubic meters. And we know that we're getting 500 cubic meters per day. All right, so then again, just doing some multiplication, how much salt are we getting every day? Well, 2.5 kilograms of salt, right? So we're always gaining 2.5 kilograms of salt per day from stream A. All right. And then what about how much salt are we losing? Well, it depends, right? And what does it depend on? Well, it's how much salt do we have in the pond? What's the rate of flow? So it's, again, just going to be concentration times the amount. The concentration of the salt is going to be the amount of salt divided by the volume. What's the volume? Well, it starts out as 10,000, but we're losing 50 every day. So it'll be 10,000 minus 50 every day. That's the concentration. We multiply that by the flow, which is 1,300 meters cubed per day. And we get this over here for our differential equation. We could simplify this. We could clean this up a little bit, right? ds dt is 2.5. I'm going to write this as a fraction just so everything's kind of consistent. This is a 1,300. Again, normally I can see where the edge of your viewing is, but because I move things around here, I can't. When we can factor out a 50 and do some cancellation here, and that's going to give us 20. Wait. All right, when you factor out, all right, so like, right, one of these zeros is going to cancel, and then we can also factor out a 5, and then the 5s are going to cancel too. So that's 26. Yeah, 26s. And then when you factor out the 5, that cancels, and we're just left with 200 minus 5t. Really shouldn't be doing this in my head. No, the 5's gone. The 5 got factored out. 200 minus t. 26s. And then I'm going to really try to make my s's not look like 5s. 26s divided by 200 minus t. And lo and behold, what do we have? We have a linear first order differential equation. It's non-homogeneous. We do not have a constant coefficient, right? The coefficient of s is a function of t. We have a constant b. We have a constant right-hand side. But the coefficient of s, remember, constant coefficient ODE means the coefficient of the variable is constant, which we do not have. But we can solve this. Oops, that's the wrong tool. We can solve, oh no. Verified disaster. We can solve this. So let's do so. Get some information about salt. All right, and let's go back to black. All right, how do we solve this? Well, let's get it in standard form first. ds dt, we'll add this over to both sides and rewrite it as 26 over 200 minus t times s equals 5/2. See how s-y this looks? I did a good job. Also, I don't want to write an equal sign there. Let's write an arrow. This is what it becomes. Now we have things in standard form, right? This is our g of t. This is our b of t. And we can use the method of integrating factors. It is a really good idea to pause the video right now and practice the integrating factors portion. We've already done the hard part together. And again, in classic differential equation style, 10 minutes of the video is just setting things up, processing the information, getting a picture, trying to write an equation. The actual new stuff, right, is going to be much shorter, probably, unless I gave you a terrible integral, which it might be fun. All right. But just again, really want you to pay good attention to this first 10 minutes, what we already did. What was our logic? How do we set things up? How do we present things? Because that's going to be the hardest part. And that's the most important part, modeling, right? Solving the models by hand is really not that important in the grand scheme of things. Computers can do that for us. But setting up the model and knowing how they work and knowing how we can analyze them, that is the important stuff. All right, so hopefully you pause the video and you have this solution and you're just checking it now. We know that the integrating factor, if there is one, is going to be e to the integral of g, which is 26 divided by 200 minus t, right? It's that g dt. So we need to integrate this, which is not as bad as it looks. We can do a substitution. I'm not going to do the full substitution, but you probably should. U is 200 minus t. Then we're going to get e to the 26. It'll become a minus 26 when we do the substitution. Minus 26, natural log of the absolute value of 200 minus t. And again, plus c. That's the integral. We can check our integral by taking the derivative. Derivative of natural log is 1 over that. Great. Times the derivative of the inside cancels the negative. Yeah, we did that right. And again, there's infinitely many answers. We can choose whatever version of c that we want. A lot of times we just choose the nicest. Oh, and actually we have an e and a c here. Let's use properties of exponentials to rewrite this. This negative 26, let's put it up here. It's kind of weird to have an exponent of negative 26, but that's fine, because now the e and the natural log cancel out. As long as the inside's positive, otherwise we have absolute value shenanigans. But we really do want the inside to be positive. Why is that? And in fact, this is something I should have done earlier when I created my differential equation. What's the domain here? Because the domain really matters. We know that as long as the right-hand side is continuous with a continuous derivative, we have a solution that exists that is also unique. You can see that there might be some problems at certain places. We're really only curious about what happens. We're not curious about the past. The past, the pond was clean until these yahoos came in, started yucking trash in. And then this model is not valid past 200 days, right? In fact, as we get close to 200 days, this gets a little sketchy. All right, so we're only looking from t in this interval. We should have done that earlier. And that's going to be really important because if t is between 0 and 200, we don't need these absolute values anymore. If t is between 0 and 200, and again, it should not equal 200. Did I do that correctly? No, I did not. It cannot equal 200. That's going to be bad. Then we don't need the absolute values. And again, we do have true cancellation. We're going to get a constant times 200 minus t to the negative 26 power, which is kind of funny. It's a funny exponent. We don't get a lot of exponents like this. So do you want c to be something? You could. All right, this is what we're going to multiply both sides of the equation by. Maybe we want to multiply both sides of the equation by 1 over 26 to get rid of that. Maybe we want to multiply both sides of the equation by 2/5 to get rid of that. You can make C be whatever you want to be. Whatever you want it to be. All right. Maybe you don't want fractions. We just let it be 2. Let's choose it to be 2. Right? We can do whatever we want. Well, within reason. This isn't the Wild West over here. But again, C can be anything. You don't have to think. You can always just make it 1 if you want. All right. So we multiply both sides by this integrating factor. That's going to give us 2 times 200 minus t to the negative 26. Plus 2 times that is going to be 52. What do we have? Well, this times that, this is going to be to the negative 27th now, right? 200 minus t to the negative 27th times s. And that's equal to 5/2 times 2 is just 5 times 200 minus t to the negative 26. So it looks a little weird, especially since I did not write my dsdt. But we should be pretty fine. All right, let's clean this up. Who did this? Call yourself a math professor. And then if we did things right, then we can rewrite this with the product rule. This should be the derivative with respect to time of the integrating factor, which is 2 times 200 minus t, so negative 26, times y, equals the right-hand side, 5 times 200 minus t to the negative 26th. Hopefully we did this right. Let's double check. What happens if we use the product rule on the left-hand side? Ugh. Might be a little messy. Uh-oh, and I might be off by a negative. Oh, no, I'm not. Chain rule. Okay, so derivative of this first thing, right, is the power rule. Negative 52 times this to the negative 27th times the negative on the inside's positive 52 times this, the negative 27th. Great. Also, again, this is not a y, it's an s. And then again, the other one is also good, right? It's just 2 times this, right? It's just the integrating factor times dsdt. Great, I did the product rule right and the integrating factor right. And now we can integrate both sides, and I'm sure it will lead to a very happy ending. So when we integrate both sides, we're going to get 2 times 200 minus t to the negative 26 power times s, the salt, is equal to the integral of the right-hand side, which looks kind of messy, but it's actually not that bad. It's just a simple u substitution, where u is equal to 200 minus t, and du is equal to negative dt. So when you do that, it's basically, there's no way I mess this up, right? Doing it in my head. But basically, it's just the power rule. So this adds a power to become negative 25. And then we have 200 minus t. And then because of the dt, it becomes positive again. And of course, if hypothetically we are worried about doing math in our head, we check our answer by taking the derivative. Derivative of this becomes negative 25 over 5 is negative 5. This becomes an exponent of negative 26. Chain rule makes it positive again. Great, I did it right. And now we're almost done. It looks kind of messy, but we just divide this over. And dividing this over, right, we have to divide both sides by 2. So it's going to make this a 10 down here, right? Going to divide both sides by 2, and then also multiply by this to the 26th power. And we're going to get s as a function of t. It's going to be 1/10 times 26, 25. Oh, it's just, really, did not expect this to be the answer. This is really nice. Then, of course, the plus c term gets a little less nice because this is also getting multiplied. It's also getting divided by 2. Constant divided by 2 is still a constant, but it's also getting multiplied by 200 minus t to the 26th power. Okay, so this term turned out really nice. This term it turned out a little less nice, right? Okay. And now we need to use the initial condition. We need to find out what C is. Remember, our initial condition was originally there was no salt in this pond. So S of 0 equals 0. We solve that real quick. We get 0 is equal to 20 plus... Wait. Really? T is equal to 0. This is C times 200 minus 0. All right, surely I've messed up. That's quite the constant of integration. Okay. It's fine though. It's fine. Everything's fine. So C is going to be negative 20 over 200 to the 26th power. And here's why this is fine. Because what does our differential equation look like? It's S of t, and again, we could distribute this. We could rewrite this, right? This is going to be 20 minus t over 10. You could keep it if you wanted to. Plus, or minus, right? We're subtracting, minus 20. And then we're multiplying by this to the 26th power. We're dividing by 200 to the 26th power. We can just put it all to the 26th power, right? This is the same thing. And again, that inside is actually quite nice. And again, we could rewrite this if we wanted to. And again, I'm checking my answer because I'm going to be smart. And this is actually correct. Even though this is a very funny constant of integration. This is the amount of salt in the pond over time. Where, again, we have pollution from the road salt. We got people throwing their trash in the pond. This is how much salt is in the pond. So let's see what this looks like. All right. Let's see what this looks like. We're going to plot the slope field for this differential equation. Let's see how we did. So the slope field is going to be for 5 halves minus 26y divided by 200 minus x. And we have the initial condition, 0, 0. So you can see that early on, this is getting cropped a little bit. Great. Early on, the salt is increasing a lot. And then this plotter is actually bugging out a little bit. What happens if I pretend that like the red continues on into the green, because this is really what should happen. I'm going to disappear real quick so you can see. The salt is actually disappearing in the pond. Right? The salt's going to 0. In 200 days, the salt will be 0. So you might think, this is great news. This is great news, because the salt from the road is disappearing. Well, slow down a little bit. This model breaks down close to 200. Remember, 200 was our domain. And why does it break down? It breaks down because what actually happens in 200 days? Okay. Well, in 200 days, we have 10,000 cubic meters of trash. We don't have a pond anymore in 200 days. They dump in so much trash. In 200 days, the pond fills up. So the amount of salt in the pond, there is no salt in the pond because there's no pond. Oh gosh. But yeah, you can see that. So there's some conclusions we could make from this. I'm not really going to spend the time on that. The book talks about it a little bit more, but here's an example, right, of what it could look like if the flow in is not the same as the flow out, and specifically also, we have a non-homogeneous equation now. If the flow in is the same as the flow out, it's autonomous, so it's separable. Since it's not that this time, we had to use integrating factors. So we got some good practice in with some weird looking functions. Cat slipped. All right, so hope you had a good time with this. I did. That was a fun example. There's some good math in here, some good setting up, some good solving. Oh man, some cool visuals. And the last video was really just kind of a little summary video. So the next video, I won't spoil it too much, but it's just kind of comparing 1.8 with 1.9. When do we like guessing and undetermined coefficients? When do we like integrating factors? Compare and contrast. It's the end of the chapter. Woohoo, celebrate. Bye-bye.